Greetings everyone, my name is Ikram Uzzaman and today we're going to look at the AVR CPU architecture and some assembly instructions for it. So first of all, why should you know the assembly language? It's because it makes us understand more about the architecture and hence help us write efficient codes. Here you can see a simplified architecture of AVR microcontroller. An important thing to notice here is the separate buses for both data and program memory. This pattern is called Harvard architecture. Here is the program memory of ATmega32. The memory organization is 16K cross 2 bytes. It means there are 16K memory locations and each location consists of 2 bytes. At the highest level there is a section for boot flash and the rest of it is for the application. Next, here is the memory map for data memory. We can divide the data memory in 3 spaces. First, from location 0 to 1F is the general purpose registers. These are the high-speed registers and the ALU, that is the arithmetic and logic unit of the CPU, has a direct access of these registers. Next, from 20 to 5F, it's the space for special purpose registers, SFR. These registers are used for manipulating I/O ports, accessing timers, interrupt, ADC unit, etc. Finally, there's space for RAM. It's also known as the scratchpad memory. AVR uses the RISC architecture. There are around 130 instructions. Let's look at some of the operations. The first one is load immediate instruction, LDI. Load immediate means to load constant data to a GPR. The full instruction consists of the opcode and operands. Here LDI is the opcode and RD and K are operands. So it's a 2-byte instruction. 4 bits are used for the opcode and 8 bits are used for the K constant, and for RD, that is 16 registers can be defined by the D values here. So we need to use R16 to R31 for the register, and a constant value of 0 to 255 can be used. Then we have the add instruction, which adds the contents of second operand with the first operand and stores the result in the first operand. That means the result will be stored in RD. The next instruction is load from data space, or LDS. It loads data from memory space to a register. The second operand indicates a memory location. It can be a both GPR, SFR, or a RAM location. The opcode consists 10 bits, 5 bits indicates a GPR, and the other 17 bits are used for the memory location. It is a 4-byte instruction, unlike LDI and add, which are 2-byte instructions. Similar to LDS, STS is also a 4-byte instruction. STS stores data from GPR to another memory location. Notice the destination is always kept first between the 2 operands. Let's look at an example. Here, the first task is to add 2 constants and store the value in a memory location 300. The second task is to load the result from 300 to R10. First of all, I'm opening the Microchip Studio. Now I'm creating a new project. I'll call it example 1. Remember to select assembler here. Let's select the chip. I'm using ATmega32. the project is being created. Okay, there are some startup codes. I will remove them. So the first task is to add two constants. To add the constants, first we need to load them into the register. So I will use R16 for loading the value 3F and R17 for 9D. Then I will add the values in R17 register. So this one is R17, and after that I need to store the result into memory location 300. So this is the first task, and then in the second task I need to load the value in R10. Let's build the project. Then I will set a breakpoint and run the project. Before that, I need to select the simulator or programmer. For now, I am simulating the project. Later, we will run it in a physical device. So let's run. So here you can see the status of various memories. So initially it's indicating the flash memory, the instructions being decoded in the flash memory. So I'll select the IRAM and let's watch the R16 register. So R16 is mapped in 10 location. So if I step into the instruction, you can see R16 is loaded with 3F. After that, R17 is loaded with 9D, and after the addition, the values are added in R16. Then if we go to the memory location 300, we can observe the result is stored in 300. And finally, at memory location A, which refers the R10 register, after this instruction is executed, the result will be stored in R10. Let's see. So this is indicating the R10 register. After stepping into, we can see R10 is loaded with the resulted value. So that's it for the video. Next, we will see some more assembly instructions and later run the code into a physical ADMega32 microcontroller. Thanks for watching.